Hello and welcome back. In this video, we're going to learn an alternative way to compute matrix times vector multiplication. First, let's see what happens when you multiply a matrix with only one row by a vector. As usual, the number of entries in the vector, which is 3 in this case, must equal the number of columns of your matrix. In this case, each one of these columns just has one number in it, but we can still deal with it like it's a regular old vector. So according to this definition, we're just going to do 1 times a vector with a 10 in it, plus a 2 times a vector with 1, 7, plus 3 times this negative 8 vector. And just to multiply a vector by a scalar, we just multiply the only entry in there by that scalar. So that gives you 10 plus 14 as a vector plus negative 24. And then we can add up these three vectors to just get one vector with a 0 in it. Now, there isn't really an important difference between a vector with one entry in it and just a number. So whenever you see a one entry vector, if you want to just erase the brackets and call it a number, you'll probably be fine. It's just a little sloppy, but it will save us from having to write some extra definitions. It's kind of like in the original definition of a times x, we pretended that each of the columns was really an individual vector, and adding those extra parentheses doesn't really mean anything different, at least as far as this linear algebra class goes. So we can just say that the result of multiplying a single row matrix by a vector is just a number. Now, with that in mind, let's look at this alternative definition for computing the result of a matrix times a vector, the row-column rule. So if you have an m by n matrix, you can take each of those m rows and think of it as an individual single row matrix. And if x is an Rn, so this is all well defined and x has the same number of entries as A has columns, then I claim that this formula here gives you the same result for A times x as the original definition. And to compute this for each one of these rows in this new vector here, each one of these is just going to be a single number because what we're doing is multiplying a single row matrix by a vector. And you just get a number for each one of those entries. So let's look at an example or an exercise for you to do actually. This is for two reasons. One, to check that you understand this notation, and two, also to help you convince yourself that the original definition and this row-column rule will give you the same result. So let's pause it here because the answers for you to check will appear in a moment. And here are those answers. Sorry about that awful pause music, but I'm a little bit worried about copyright infringement. I need to find a solution for that. Anyways, here's the answers. With the first one, hopefully you got -1, 1, -4, -8 when you did it both ways. And the important thing is that you can kind of see that the arithmetic you're doing works out the same way both ways. Like we ended up doing 1 times 2 minus 1 times 3 to calculate that -1, just like here we did 1 times 2 minus 1 times 3. And that should hopefully convince you that the row-column rule does always give you the same result as the original definition. This is actually a special matrix. It's called the identity matrix. This matrix has the property that whenever you multiply it by any old R3 vector, such as this weird one, it doesn't change it. The result is exactly the same as your original vector. So that's that. Have a good day.